Yeah, okay. Can you hear me now?
Yes, sir.
Yes.
Okay, okay. Yeah, so uh, yeah, so we discussed talking about what did we do? So in the beginning, we talked about some measures of information, and we talked about mutual information. So that is where we started with mutual information, and then we talked about entropy. Okay, these are the main two things we discussed, and then we started talking about source coding theorem, source coding theorem, and we talked about construction of an optimal code. So optimal in a sense that a code is optimal if there is no other code whose expected code word length is less or strictly less than the expected code word length of the optimal code. Okay, so yeah, so coding theorem, and we talked about Hoffman's code. Okay, Hoffman's code. So now, so if you remember the picture we talked about, yeah. So this is our channel, and this is the communication system. So this is very simplified picture of the entire communication system. So we talked about this part, that there are some symbols A1, A2, AK, and we talked about how to encode this in terms of uh, strings of binary digits. Okay, and now we'll talk about the channel, and this channel is noisy. Okay, noisy. Our goal is, so they say, if you remember the first class, so we talked about transmitting messages. Okay, so messages, so a message means what? A message means a sequence of alphabets. Okay, a sequence of letters. Okay, so for example, if you write an email, okay, so it is nothing but a sequence of alphabets. If you consider space is also an alphabet, let's say, so it is nothing but a sequence of letters, alphabets. Okay, so when we are transmitting this, okay, this noise is this channel is noisy, but we want to transmit this reliably. So we want to have a reliable communication system, meaning whatever we wanted to send through this channel, okay, the same message has to be received by the receiver. So this is the sender, and this is the receiver. Okay, and our idea will be the main concern about the theory, our discourse is, or in general, the subject is how to design, or what should be the principle, okay, of designing of communication system. Okay, so yeah, so we talked about this part, and now we'll talk about the channel. So we talked about this part, and now we talked about the channel, the noisy channel part. Okay, okay, so we had seen an example of a channel, which is, let's say, the binary symmetric channel, and we said, okay, this channel, or the transmission channel, okay, can be defined in terms of the set of inputs, okay, uh, at the information source, and the set of outputs available, okay, at the output source, okay, or output. Guys, just a minute. I think somebody is knocking at the door. I'll just come back. Yeah. So in that example, we said a channel, okay, can be described by these conditional probabilities. Okay. Suppose A1, A2, AK, and here is some, like say B1, B2, BJ. Okay. And then the channel is described by, let's say, what is the probability of, let's say, obtaining some BJ when some AK is sent. Okay. So yeah, so the channel is described by this conditional probabilities. Okay. And okay, there are many kinds of channels, but we'll right now we'll only focus on, there is something called discrete memoryless channel. Okay. So earlier we had discrete memoryless source. So where what happens is, if you create a source sequence, then the letters, okay, are the terms of the sequence, okay, they are independent. They are stochastically statistically independent. Okay. So in if you construct, let's say, some A1, A2, some AL sequence of L alphabets or letters or source alphabets, then the choice of this A2, okay, so instead of A2 it could be A3, A4, whatever it is. So the choice of this is independent of the choice of the first letter in the sequence. Okay. So this was the meaning of memoryless source. Now we'll talk about a memoryless channel. So this also, our focus will be on discrete memoryless memoryless channel. And in this channel, actually, I will formally define it, but let me just give you an informal meaning of this. So the thing is, if I send a sequence, let's say x1, x2, xn, and let's say output is some y1, y2, let's say yn, okay, then the output letter, let's say y1, okay, okay, should depend on x1. The input, so first output, let's say in this sequence, so the first letter in this output sequence. So this is input, and this is, let's say, output. So channel means, so this output depends only on input x1. This we'll give examples. We'll discuss this. So any pick, if you pick some yj, okay, so that would only depend on xj. Okay, so this is some. So this is an, it's informal way of saying it is a memoryless. So it does not. So yj does not depend on other inputs except the j, except the jth one. Okay. Okay. So now I mean. If I give you now a brief diagram of the communication channel in much more detail, what is happening is, I mean, we'll just recall what we are doing. Okay, so so what happens is, here you have source, here you have source, and here you have this coder. Okay, so which will code. Okay, so let's say this is discrete. Okay, the source is discrete. So coder means it will code these letters in terms of some binary sequence. Okay. And then what happens is, there is something called digital data modular. Okay, and then we have a waveform here, because when I'm transmitting this using some technology, some communication system like satellite communication, whatever it is. So then this has to be waveform. So let me write it here, waveform. So this is waveform, and here we actually have a continuous time channel, continuous time channel. And then so some waveform will be received here, which is demodulator. So this is digital data demodulator, demodulator. And then we have a decoder here, decoder, and I can say this is also discrete because the output is discrete because discrete. This is also discrete actually. And then we have this sort destination. Okay. So we are not, for example, talking about, so what we are talking about is this part basically. So this is what is the discrete channel. So here the input is discrete. Here is the input. Okay, let's say here is the input and here is the output. So we are not focusing on this particular part. Okay. So we are not focusing on this particular part. What is happening here? Okay. For our case, we are giving input as a set of sequences or discrete sequences or just sequences of letters or binary digits, and at the destination we are receiving also a sequence of binary digits. And here what is going on inside this continuous part we are not discussing, because if we want to discuss this continuous part, again we have to define other things here. Okay, so our focus is on this discrete part. Okay, so that's why we are saying is a discrete memoryless channel, because our input is discrete and our output is also discrete. Okay, so this local part we are avoiding, this continuous time channel. Okay, so yeah, so channel can be both actually. Okay, discrete and continuous. Anyway, okay, so okay, I'm talking about memoryless channel. So that means there is also a version of channels with memory. Okay, so which we are not going to discuss probably in this course. We'll not have time to do that. But there is something called channels with memory. Okay, let me just write it down. So there is something called channels with memory. Okay, yeah. And memory meaning what is happening if you have a memory, channel with memory means it is a complement of memoryless. In a memoryless channel, what is happening? Yj depends only on xj. Okay, but if you have a channel with memory, so yj can also depend. Okay, not only depends on xj but also on other inputs, maybe xj minus 1, xj minus 2. Okay, and so on. So yeah, so channels with memory means output, the jth output, okay, depends on more than one current input or more than our previous inputs. Okay, yeah. Okay, so let us now go to our setup discrete memoryless channel. Okay, so this is the picture we should keep in mind whenever we are talking about this discrete memoryless channel. Okay, so what we'll do is we'll assume that this is my source and this is my sink or my destination. Okay, this is my source and this is my destination. Okay, and this is my channel. A simplified picture of everything. And here I'll consider my inputs as integers. Okay, you need not take integers, you can just take a1, a2, ak, but because we talked about a1, a2, ak as symbols, and here we can talk about here, like after coding we have a sequence of 0 1s, but sequence of 0 1s can be used to construct an integer, let's say. Okay, if I give you a bunch of 0 1s, you can of course construct an integer corresponding to that. Okay, so let me call, or just for the sake of, let's say, notational convenience. Okay, I'm assuming that the inputs, okay, the input alphabet, okay, that contains some integers, and let's say the integers are like 0, okay, 1, and up to, let's say, k minus 1. And the outputs are, let's say, also integers 0, 1, and let's say j minus 1. So here my variable is some k. I'll denote it some k, so small k. Okay, and here my variable is j. Okay, these two things are important. Okay, k and j. So, and how this channel is specified? This is probability of getting some j given some k, okay, where k is equal to 1 to up to 0 to up to k minus 1. Okay, this is how the channel is described. Okay, yeah, and we also always say, so I'm just setting up the notations. So we always write small x bar. Okay, this is my input sequence. Okay, this is, let's say I'll write x1, x2. By the way, this channel coding. So we'll prove finally what is channel coding theorem. Okay, but here these notations will be a little bit complicated than the previous one. Okay, than the source coding part. Okay, so that's why first of all I'm defining all the notations. Okay, what I'm going to use. So this small x bar is just x1, x2, xn. This xi's, okay, or let's say all xn, okay, or maybe I can also write uh, begin here. Okay, so xn, so 1 less equal to n less equal to, let's say, capital N. Okay, so this xn, this is some 0 to up to k minus 1. Okay, this set. So this is an element. So xon is is a source letter. Here it is 0, 1 or k minus 1. Similarly, here it is 0 up to 1 k minus 1. Here it is the same. So all this xn, x small n, so they are one of these 0, 1 up to n minus 1. And same thing is also true for the output. Okay, so the output sequence, which let me write it like y bar, small y bar, which is, let's say, y1, y2 up to some yn. And here, of course, yi's are, let's say, yn. Okay, this belongs to what, 0, 1 up to j minus 1 for all n, small n, from 1 to up to capital N. Okay. Now, say this channel was for defined for, let's say, for individual terms, right? Like if some k is obtained, what is the probability that that j was sent? Okay, sorry, I mean j is obtained. What is the probability that k was sent? This is the conditional probability. So this is like individual letters. Okay. Now, if I am transmitting a sequence of letters, okay, sequence of letters, then that means we have to talk about the transition probability. We have to talk about probability. Okay, so probability of, let's say, yn and xn. Okay, so that means this yn is a term here. Okay, and xn is a term here. And when we have memoryless channel, we basically focus on this part. Okay, whereas the probability of getting yn when yn when x1 is sent. Okay, so this is what is the transition probability, which is important. The transition probability, transition probability. Okay, probability. Now I'm in a position to define mathematically what is called the memoryless channel. Okay, so the definition. Okay, the channel. So with all this setup, whenever I say channel now, this is my setup. Okay, everything is my set, all this notation. Now the channel, okay, is called memoryless. Okay, if each output letter, okay, in the sequence, in the input sequence or in the output sequence, okay, depends, okay, only on the corresponding okay input. So what do I mean by this then? If I write probability of this n, I'm writing, say here in my notation, this n, capital N, I'm writing because the length of the sequence is n, capital N. Okay. So what I'm saying now, if I write this condition mathematically, it means y bar given x bar, what it should be. So y bar here, you see, y bar here is y1, y2, yn given x1, x2, xn. X bar means x1, x2, xn, and y bar means y1, y2, yn. And I'm saying this probability should depend only on this probabilities, like individual letter probabilities. Okay, then what should I write this? Mathematical, what should be my definition of memoryless channel? Any idea? Okay, so let me define it. This is nothing but product of probability of yn xn, n equal to 1 to n, capital N. So this is the mathematical criteria of calling this channel to be memoryless. Okay, so that if I even if I send a sequence x1, x2, xn, and if I receive y1, y2, yn, then y small yn depends on small xn. Small yn does not depend on others. So if I consider this conditional probability, then what is the probability that I'll get y bar when x bar is sent? This is just the product of the individual conditional probabilities. Okay, this is what is the mathematical definition of memoryless. Okay, and this has to be satisfied. So this that is this. Okay, for this is true for all n and n. So you can n, this n could be 5, 4, 6, what does not matter. Okay, you send a sequence, okay, the input sequence of length 5, length 6, length 100, 10, 1000 doesn't matter. Okay, so it should be independent of that n. Okay, and of course it should also be independent of for all n, and also let's say x bar and y bar. Doesn't matter whatever sequence you send, doesn't matter. So let me just give you an example. I mean, I'll choose a very simple example, which is our binary symmetric channel. Okay, the example. So by memoryless, okay, let us consider this binary symmetric channel. So for binary symmetric channel, we had only two source letters, 0 and 1. And also I had 0 and 1. Okay, and then there is a probability that I'll get 0 when 0 is sent, and there is a probability that I'll get 1 when 0 is sent. And let us say the probabilities are like this. This is 0.9. So the other one should be 0.1. Okay, so same thing is here. And since this is symmetric, let us say, so this is also 0.9. So there's high probability that if 0 is sent, then 0 is also received. Okay, with high probability 0.9. Now, if you consider this binary symmetric channel, so what I'm saying is basically probability of 0 given 0, it is 0.9. Probability of 1 given 0 is 0.1. So this is the definition of the channel. So probability of 0 when 1 is sent is 0.1, and probability of 1 given 1 equal to 0.9. Now, if I say if the binary symmetric channel, okay, is memoryless, then what will happen? Memoryless, then what happens? Then suppose I construct a sequence of length 2, then my question is, what is the probability of 0, 0, send 0, 0? What will be this one? So here, x bar is equal to 0, 0. This is, let's say, x bar, and this is, let's say, y bar. Okay, so then what if it is memoryless, then what will happen? This would be equal to probability of 0 given 0 times probability of 0 given 0. So this should be equal to 0.9 whole square. Now, if I ask, okay, what is the probability of, let's say, 1 0 given 0 0? That means this is x bar, 0 0, okay, is sent and 1 0 is received. This should be what? This should be probability of, whatever this one, 1 given 0 times probability of 0 given 0. So that means it is that 0.1 times 0.9. Similarly, if I ask you to find, let's say, what is the probability of 1 1 sending 0 0, I mean you understood, right? So okay, let's let me write one more. Then it is 1 given 0 times probability of 1 given 0. So this is 0.1 whole square. Okay, so what is the meaning of that? Meaning is the probability of receiving, okay, the sequence, let's say 0 0, which is, let's say, y bar, okay, when it's x bar, which is 0 0, is transmitted. Okay, so this is the meaning of this memoryless channel. Okay, now the main theme of understanding a channel is, okay, that, okay, suppose you send, okay, so before that, let me say, when we say the channel, we said, okay, so there are, so let's say there are some input letters here, okay, source letters, and there are some, let's say, some output letters, and you can have, let's say, these probabilities, okay, and you can have also these probabilities. Now there is one more probability which is similarly this one and this one, okay, let's say, I mean, I'm just giving an example, okay, so this is, let's say, x, and this is, let's say, y, okay. Now what you said is, and when we talked about mutual information, okay, so when you said we have a channel, then we said, okay, there is something called mutual information which will measure the uncertainty about two random variable. Okay, this is mutual, x and this y here. So here this y is the output random variable, represents, let's say, output random variable, and x represents the input random variable. And there we had seen that we talked about what is called the average mutual information. Okay, so can anybody tell me what is the meaning of average mutual information? Do you recall anything? Can you guys hear me? Can you hear me?
Yes,
Yes,
sir.
sir.
Okay, so what was average mutual information of two random variables? What does it mean? Or if I just tell you what is the average information between mutual information between two variables, two numbers x and y. X is a possible input and y is a possible output. So what was that? What was I, x, this one? What was the meaning? This is one of the first thing which we introduced, okay, about channel, okay, and first we introduced the concept of mutual information of two possible outcomes, x and y, and then we put that definition in the context of a channel. So what is the meaning of ix semicolon y, the mutual information between x and y, and then if you take the average, then we talked about I x given y. Right, so what is the meaning of that? What is the meaning of this one?
So log of probability of x given y by probability of x.
Yeah.
And if we
Yeah. So no, what I'm saying is what does it mean? Okay, so can you repeat that again? What is the definition? Log of.
probability of x given y
Okay.
by probability of x.
Okay. And what does it measure? It's a log 2. Let us assume log 2. What does it measure? Or
So it's measure the information given by X if Y has already occurred.
okay, so it means like how much information X contains about Y. And we also had seen that this is exactly equal to Y. This was symmetric. This was mutual, right? So this is the same. That means how much Y, how much intent or the content of information, okay, how much information about X, okay, does Y contain? Same thing as saying how much information about Y does X contain, okay? So this is symmetric, okay? Yeah, so this is kind of mutual, okay? We talked about that. And then when I define this term, okay, for the entire random variable X and Y, then we said it is the average of all the mutual information. So what was the definition of this one? If I take the average mean, it's the expected value, right? So what is the expected value? What should we do? Anybody remembers?
We have to take the sum over all x y.
Okay, and then so
Then
average meaning, yeah.
probability of x y into I of x colon y.
Okay, okay, overall xy. Okay, now, yeah. So this is the mutual limit. So here, what is the meaning of that? Informal meaning of this is how much information about the random variable y, okay, does x, the random variable x contain? Same thing, okay, for y given x, or maybe same thing you can say about this. Okay, so this was my definition. Okay, now here we revisit this concept again because the channel capacity, okay, depends on mutual information. In fact, we will define channel capacity in terms of mutual information only. Okay, but before that, so this was our, so this just I just recall whatever we discussed before. But now before I discuss, before I define capacity of the channel, let me introduce one more notation. So here everything was, so I think we use the same notation, Lapus xy, then this is pxy, okay? And then I is again here p. Now p is used everywhere, but all these p's are different. For example, here, this is the probability distribution on the joint random variable xy. And this probability here in the mutual definition, this is x given y. This is on the conditional random variable. And this in the denominator, it is random variable for x. So they are all different probabilities, but we used to write only one p to mean everything. Okay, but now we'll introduce separately. I mean, we'll use notation, separate notation for the probability distribution of x or for the joint probability distribution. Okay, so we'll use a different notation. So we'll not use p for everything because there will be there will be a chance of confusion. Okay, so so did you get me what I said? Did I make any sense? So I said, okay, let me just repeat. So here, okay, let me write it here. So if I just, so I have to take here a double function basically. You can take y or x, doesn't matter. And then here I have to write, let's say pxy xy, okay, and then log 2 of p x y x given y, and this is p x x. Now what I'm okay, I can further write this down. Let's say x and this is y, because here in terms of these two probabilities, I can again write it as a product of these two. So I can write it like p x x times p, right, y given x. So x given uh, so y given x, okay, and then this is log 2. P x given y, and P of x, x. So now see here I'm denoting it a P of x means, let's say P of x means the probability distribution of the random variable x. Here probability distribution of the random variable, conditional random variable y given x. Here probability distribution of the random variable x given y, and here again x. So I am using P for everything. Okay. In fact, when I define this one, we also did not write this subscripts here. Okay, because it is clear from this many. But here, because there will be many probabilities on many random variables, you'll see little later. So let us now specifically mention, use different notations, so separate notation for separate random variable. Okay, so yeah. So let me first introduce the notations which we'll be considering. So we'll write QK. Okay. So we'll write this as the probability distribution. Okay, for the input source, for the inputs. Okay, for the inputs, and we'll just write P because P is the prime thing here. J given K. Okay, J given K. So here you see my channel. Here we said the outputs are 1 to up to j. So we'll use this variable small j for the output, and for the input we'll write small k. Okay, so the probability is p j given k. So we'll write the same. So the transmission probability. So this is my notation for transmission probability. Transmission. Okay, probability. Now let me define what is the average mutual information for any two random variable in terms of these two notations. Okay, so I'll just use the same definition here. Okay, just I'm changing the notation. So this is nothing but sum over k equal to 0 to k minus 1, sum over j equal to 0 to j minus 1, and then qk, then p of j given k log of pj given k, and is there any mistake here in the definition? Hmm?
That will be k given j in the numerator.
In the numerator k given j, no? Okay, yeah. So okay, let me is it k given j, right? What did we write? No, it is j given k, right? So j, what is the probability? What is the probability of getting j as an output?
Yeah, we can write
So
in either way because the both will be same. It's
no. Here j is the output. Okay, so what is the probability that I will get the output j when k is sent, small k is sent, right? So this is okay. So if I want to write this now, so I have to do some manipulation here, it seems. So if I write, okay, so let me just, because notation actually is very dangerous. I mean, whenever you're writing this, you have to be really careful because it will mean, otherwise it will mean something else. Okay, so now if I write this as this, probability of, let's say, k given j, right? This is what our definition was, k given j, and this was probability of Oh, so here it will be q. If you write like that, q k, then what is happening? Mm, okay, but we don't want to do that. Okay, because the transmission properties, they are defined in terms of pj given k, right? So how do I change this? Okay, before I do that, okay, I will change that. But before I do that, let's say now let us recall one thing. So let's recall this. Let's recall this notation. This is input, and this let's say this is output. So if we know the probability distribution of this, let's say this is qk, and if we know the transmission probabilities, let's say, okay, this is let's say p j given k, then what can we say about the probability distribution, okay, of this random variable? Or should be that one? Hmm?
Sir, we have to take the summation qk into probability
Okay,
of j given k.
yeah. So if I write this, let's say probability of j, I'm defining, okay, probability of j. In fact, yeah, probability of j, if I want to define it, then what will be this one? In terms of this notation, q and p, what should be this one?
The product of q of k into probability of j given k.
Okay, q times k into probability of j given k, right?
And we have to
And
take the
this
sum over k.
k, yes, correct. Now see, we don't want to have this one right here. In fact, we want pj given k, right? So how to change that? So see, this term here is basically p p k given j by qk, let's say. This is nothing but p kj, okay, this is a joint variable, distribution for the joint one, let's say, by qk, and let's say q some pj, right? Pj. But this same thing, I can write it as, write it as p jk by uh, jk by let's say qk pj, which is same thing as probability of j given k by probability of j. Is that okay?
Yes, sir.
Yeah. So now we can replace this here. Then we have an expression in terms of the transmission probabilities. So, so if I use that, then what we'll have? So if I use this, just a minute. So if I use this, then my average mutual information is nothing but sum over k is equal to 0 to k minus 1, sum is equal to j equal to 0 to j minus 1, and then qk, what was that? Pj given k, then log 2. Okay, this is different, okay? This is different, okay? So, yeah, and this is different. Okay, so log 2, now I will write p j given k divided by pj, but this pj is nothing but this one. So let me write it in terms of this. Sum, or let's say I equal to 0 to k minus 1, some qi and p j given I. Or you can write small k, doesn't matter. But I'm not writing small k because small k is varying here. Okay, so small k is varying. Then this k will also apply here if I write k. But this is a constant. Okay, so this is a constant. This term does not depend on this k. So instead of writing small k, I'm just writing small I. Okay, so this is my mutual average mutual information between the output and the input random variable. And now I am ready to define what is called the capacity of a discrete memoryless channel. Okay, and I'll tell you also what is the significance of that. But before that, let us define what is capacity of a channel. Now see, observe one thing. If you if you design a channel that can be used for different sources, I mean different sources meaning for different probability distributions on the input random variable, or inputs are the source symbols. I mean, if we change the source symbol, let's say, okay, suppose you want to use a channel for two different contexts. Okay, one is for some purpose, okay, and the other one is completely in a different purpose. And you can have a situation where in particular one purpose you can have frequency of some letters, okay, is different from the frequency of those letters for the other for that other purpose. Okay, so what I wanted to say is one channel can be used for many purposes. So when I am saying many purposes, that means for many probability distribution. So basically, if you want to study the property of the channel, okay, property of the channel, then the thing is it has to be independent, or it has to be in terms of in terms of the input probability distribution. So if I want to define the characteristic of a channel, okay, that has to be something, okay, which is independent of these probability distributions, because the probability distribution can vary of the input random variable, okay, or some quantity. So if you want to define the characteristics of the channel, somehow you have to consider, okay, some, I mean, some kind of a maximum over all possible probability distribution of the input random variable. So in fact, this capacity, okay, now I'm defining this capacity of a channel or of a DMC. Okay, DMC means discrete memoryless channel. Okay, I'll define it like this way. This is the largest, okay, the largest average mutual information mission. So what I'm saying is, okay, let me say my channel is fixed here. Okay, this is my channel C. I use one particular distribution, let's say some P1. I use some P1 distribution. So then I receive some, so I'm sending X and then there is some Y. Okay, so I'll receive some Y. Okay, then there will be a mutual information between X and Y. Now I change my probability distribution. Then there will also be a mutual information between X and Y. Then again I change my distribution P3. Then again I will have a mutual information. Now the property of the channel has to be the maximum information, mutual information, okay, that can be achieved over all the probability distribution you can consider on the input random variable. So the largest average mutual information, okay, that can be obtained, or let's say that can be yeah, obtained over the channel. So what I'm defining, let me write C is my channel capacity. This is channel. C is the capacity of the channel. This I'm defining this over In my notation, this is max over Q0, Q1, Q k minus 1. Max over Q, basically. And then I of xy. So I of xy, let me write it down, whatever I wrote it. Kj, Qk, okay, probability of j given k, probability of j given k, log of probability of j given k by sum over I equal to 0 to k minus 1. Okay. And then here it was qi and probability of j given I. So this is what is called the capacity. So when I'm saying this is varying over this, it means I have to optimize. So this is an optimization problem. If I want to find out capacity of a channel, capacity of a channel means is, let's say a channel is given to you. So channel is given to you means there are two probabilities which are given to you. One is the transition probabilities, okay, and another is, let's say, input. Okay. Now suppose only the transition probability is given to you, that means the channel is defined. So now you have to maximize this quantity, okay, over all q. So that means I have to maximize the function, and this is my function, okay, which is I x given y. I mean x semicolon y, the average mutual information, and the constant we have to maximize this over with the constant. Constant, you can say there are k numbers, okay, and all these numbers, let's say, if I write it like qk are bigger or equal to 0, and sum of this qk is equal to 1. Okay, so this is what it is. A qk here, I mean just qk here is nothing but q of k, let's say. Okay, k equal to 1 to sorry, 0 to k minus 1. Okay, so this is what we have to find out. So you have to solve basically a maximization problem, and if I find that, then this is the capacity of the channel. Okay, now before I go into the interpreted meaning of this, okay, the first thing to answer is, okay, from the mathematics point of view, does this exist? Does this exist means what? Does this maximum exist? Who can tell me the answer? I don't want to do that, but I will do it, but not now, later. When I'll give you some examples of channels, and then I'll compute its capacities. Okay, then we'll see how we'll go about it. But can anybody tell me why does the maximum exist here? I mean, what kind of functions you can optimize, and you will always get a maximum, or let's say minimum, whatever. What is, let's say, a sufficient condition that if this is given to you, you want to, so what do you study in optimization theory? You want to maximize, let's say, some function, okay, some function. Here it is a function of q1, q2, qk, let's say, okay, so some x1, x2, xn, let's say, and then this xi satisfies some condition. So let's say, okay, let's say some feasible region f. Then you talk about finding out the maximum, and let's say this is a real valued function, okay, meaning there is an ordering. There is maximum means others are lower than that, right? There is an ordering. So under what condition, let's say, you can say the maximum would exist? What is the sufficient condition? This is math 1, undergraduate. Hmm? Any sufficient condition of occurrence of maximum?
Sir, Hessian should be negative.
Hessian? Hessian of what? What is
F.
Hessian? Okay. Anybody else? Is there any student whose background is mathematics? Is there anyone? Meaning has done undergraduate in mathematics? No. Okay, so then let me just write it down and then you have to justify. Okay, I'm just giving you a sufficient condition, meaning I'll give you a condition if the function satisfies that and the constraint set, the feasible region satisfies that, then always maximum value exists. Okay, so if the function, okay, is continuous and defined on a compact set, or maybe let us say on a closed and bounded set. So the domain, the feasible region, let's say, is a closed bounded set, then maximum always exist. So you have to show that this function here, this is a function in terms of this q1, q2, qk minus 1. This is a continuous function. And this is a closed and bounded set. And this is simple. In fact, I already discussed this. Can anybody tell me why this is, say, if you, okay. Can anybody tell me this one? This I discussed when I talked about divergence. So when I talked about, if I just remember, dp this, okay, I talked about divergence, then that time I said. But can anybody tell me why this set is closed and bounded? This is, let's say, a k dimensional set, okay? Because there are, I mean, this entire Q, the probability distribution can be thought of as k tuple vectors, the vector space we talked about, right? K tuple vectors that you have Q1, Q2. So basically what we have is Q0, Q1. So this is the probability vector or the probability distribution. It's Q k minus 1 such that Q0 is bigger or equal to 0 and sum of this Qi, or let's say Qk, k equal to 0 to k minus 1 is equal to 1. This set. So this set is actually the domain of this function. Now, if k equal to, let's say, 2, if k equal to 2, then you can plot it, right? What is that? If k is equal to 2, capital K is equal to 2, then it is here the domain. Then what is this set? How does it look like? K is equal to 2. That means all two-dimensional vectors. K equal to 2 means what? It's just this. Some you can write small q0 and q1 such that q0, q1 are bigger or equal to 0 and q0 plus q1 is equal to 1. What is the set? This set here in this, or you can say this is the set of pairs. Here also you can say q0, q1. Yeah. What is that set here on the plane?
The straight line x plus y equals 1 on the first quadrant.
Yeah. So here, this is, let's say, q0 axis. This is q1. Okay. So any point here. So and this set is, let's say, this line equation of this line is this. Okay. So this is positive or non-negative, and this is also non-negative. So this has corresponding values here. Okay. Let's say here, this is 1 point. You can say this is 1 point and so on. Okay. These are the points. And this set is, of course, bounded and closed. Okay. I'll not define what is closed here. Okay. Bounded is, of course, it is. This is bounded, meaning it is not infinitely extended, right? This is finitely extended up to this to this. There's a bounded region. Okay, region means this is just a line segment here. The same thing you can say instead of the line segment in general for a higher dimension, it will be a plane, a finite plane. Okay, and which is bounded, so it will be in the first quadrant. Okay, if you have a notion of quadrant in that k-dimensional space, it will be just the first quadrant. Okay. If you, even you can also try to draw it when you have a three-dimensional thing. Okay. Oh, you can just draw it like this, this, and this. Okay. And then you can try to draw it like it will be like this. So this will be the plane, the finite plane. Okay, so it will be q0 plus q1 plus q2, which will be equal to 1. It will be a two-dimensional plane. Why it is two-dimensional? Because there is 2 degrees of freedom. So it is, let's say q0, it is q1, it is q2. So similarly, so this is just this plane. So you can higher the dimension, you can say that this is closed and bounded set. Okay, this is finite. Okay, so let us, okay, so this is your job is now to prove that this function is continuous. Okay, but I'll not prove this continuity. Okay, in fact, I'll use some other tool. But let us assume then that this maximum exists. Okay, and then we have to find this maximum, and that will give you the capacity. Now, what is the meaning when you say that this is the capacity? Okay, so just remember that we said we can communicate, we can transmit, okay, the data, the input data, let's say, through the noisy channel, okay, reliably. And the meaning of the channel capacity is, okay, the data which you are transmitting, okay, the data which you are transmitting reliably over the channel. So you have to transmit the data at a rate. Rate means per unit time, okay, and that rate has to be below the capacity. Then that is what is actually meant by reliable. Then only that communication will be reliable. Okay, and I'll talk about reliability of this thing, reliable channel, or okay, I'll talk about that later also. But when you are saying transmitting reliably, by reliable here, it means that the rate through which you are transmitting the data, the rate is below the capacity of the channel. Okay, that's why it is very, very fundamental. Okay, in communication. Okay. In fact, we will prove something, and this is what is called actually the channel coding theorem. And the converse of the channel coding theorem is like if you transmit the data, okay, in a rate. I will define also what is called a rate, by the way. In a rate means you say like how many number of bits you are sending, let's say, per unit time. Something like that is called a rate. Okay, I'll define what is the rate of a channel. But the converse of the channel coding theorem is if you transmit or communicate the data whose rate is more than the capacity of the channel, then the communication will not be reliable. Okay, that is also true. So the converse of or inverse of this channel coding theorem. Okay, so that's why this is very, very fundamental. So before that, before going to proving those converse or the source coding theorem, because yeah, we need to develop a little bit. We need to prove some results. Let's say, okay, before we go into the source coding theorem. Okay. Okay. So let us. This is our first theorem now. First theorem. The first. Okay. So here. So let. So now see here. What we'll do is. What is our goal here? We are transmitting data through a noisy channel. Okay. And here we'll talk about transmitting data. Okay. Via sequences. Because when you are sending a word, let's say a word, okay, so a word contains more than one word, one letter, let's say some finite number of letters, n number of letters, let's say, will give you a word. Okay, so what we're trying to do first here, if you send a sequence, let's say x bar, okay, x bar, let's say it is x1, x2, xn, and suppose receive y bar, which is y1, y2, yn, then the mutual information, okay, of this, so let's say mutual information, this, okay, how it is related to the mutual information of the individual terms of the sequence. So how it is related to this? Some xn, yn. What is the connection? How do I write this in terms of this? Okay, this is our first result. Okay, so instead of writing this x bar here, let us consider the random variable. Okay, so first let us assume that there is a probability distribution in the input. Okay, so let qn x bar, okay, be, whenever, okay, be the probability distribution on sequences of n inputs or n input letters. Okay, in a discrete memoryless channel in a DMC is the first thing. Now let x bar to the power n, this is capital X bar, okay, and y bar capital N, this is capital Y, okay, denote denote okay the denote the random variable corresponding to, okay, corresponding to the sequence of, okay, sequence of input or maybe input and output sequence corresponding to input and output sequences respectively. So what do I mean by that? So I'm saying, I mean, many things here. Okay. First of all, Q and X bar, what is that? See, all this X1, X2, Xn, let's say, they belong to, say, just recall, all these Xi's, they are in this 0, 1 up to K minus 1. All these Yi, they belong to 0, 1 up to some J minus 1. Now, what is Q and X bar? X bar is nothing but sequences of Xi. So that means you are constructing X1, X2, Xn. And all these Xi's can take a value. So here, this is a set basically. 0. So Xi can take this value. 0 to up to K minus 1. So you have this set. So these are all possible inputs. Then it also should have a probability distribution, meaning these are all the sample points for your sequence, for your inputs. So there must be a probability distribution associated with this sample space. And that probability distribution is defined by Qn. Okay, that's the first thing. Second thing is, when I write Xn bar, okay, now when I write Xn bar, this is basically this random variable, the joint random variable, x1, x2, xn. And whenever I write y bar n, this is y1, y2, yn. Okay, so then there is also a joint distribution of this x1, x2, xn and y2 into in, and this represents that random variable. This represents that random variable. Okay, and each of this is also a random variable. So each random variable will also have a distribution. Okay. Now, if this everything is defined, then for a discrete memoryless channel, then I'm saying this is the conclusion of the theorem. Then I of this, the conclusion is very, very simple. I mean, conclusion will be very clear when I write it down. Is this average mutual information of Xa xn, okay, and yn, okay, this is less equal to sum over n equal to 1 to n I of xn given yn. So what does it say? If I consider this joint random variable as a whole, because see x bar n meaning all possible sequences of all possible realizations of say x1, you are treating a random variable. X1 is what? That corresponds to this x1, and x1 can take any value from this. Similarly, x2 is a random variable. Why? Because x2 can take any value here, and that can take from these values here 1 to up to k minus 1. So this each x1 is a random variable. Now there is a corresponding random variable also y1, y2, yn. Now if your input is x1, let's say your input is x1, x2 dot 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 xn, and your output is y1, y2, yn, and you do it for all possible x1, x2, xn. This all possible is actually given by this one as a joint, all possible. So here it will be xn bar n, here it will be y bar n. So this is the mutual information of this joint random variables. And what the theorem says, this is always less equal to the sum of the corresponding individual random variables. Because all this, so there is an individual random variable. For small x1, you have capital X1. For small x2, you have capital X2, and so on. These are individual random variables, and here you have individual random variables. So it says the mutual information of the joint random variables, okay, is less equal to sum of the mutual information, okay, between the individual random variable, because it is memoryless. Okay. Now it says more. Now it says furthermore. In fact, it gives a bound about the channel capacity. It says, okay, it says yeah, and I x bar n y bar n is less equal to n times the channel capacity. So the channel capacity is bigger equal to 1 by capital N times this. So now we have a lower bound for the channel capacity. The channel capacity is bigger equal to this mutual information divided by capital N. Capital N is the length of the source sequence, and or you can say the input sequence and the output sequence. Okay, there is a meaning. I mean, the conclusion is very, very clear, although there are some, I mean, if you are habituated starting probability statistics, random variable, okay, these are all random vectors, by the way. So if you are habituated, then this is not a problem. Otherwise, you have to be a little slow, okay, to understand what it means when I'm writing all this. Okay, so x bar n is the joint random variable x1, x2, xn, and this each x1, x2, xn is again a random variable, and trying to measure the mutual information. What does this contain? Y1, the mutual information between this individual, okay, random variables, and the mutual information about the whole, the joint one. This is given by the first equation here. The second equation gives a bound about the channel capacity. Okay, we have 8 minutes left, but I don't think I'll be able to finish the proof. So I think we'll stop here because I have to organize a seminar from 3:30 to 6:30, okay, in the department. So I have to be there. So I'll stop here. And you can, if you have any question, you can ask me now. And channel capacity, I would say, is one of the fundamental concepts in information theory.